The South Lancashire coast, an area of shallow seas, broad sandy beaches, and the Ainsdale Dunes, a confusion of arid sandhills and waterlogged hollows, of shifting sand and standing water, of poor grassland and coniferous plantations. At ground level, an apparently chaotic environment, but one which does in fact possess both order and form. An order and form produced by the interaction between wind, vegetation, and moving sand. We'll examine this relationship and start by concentrating on the sand, and in particular on how and why it moves. Dr. John Pethick of Hull University.
In order to explain just why it happens, we'll have to use a piece of apparatus. And over here we have this thing, which is in fact a bank of what are called hot wire anemometers. They measure wind speed by recording the changes in temperature in a small wire inside this hole. We're going to take simultaneous readings of wind speed at 3 different heights above the ground surface here. We take them on these recording dials here.
The sensor 1 meter above the ground reads 5.9 meters per second. At the same time, at a height of 48 centimeters, the reading is 5.3, while at 23 centimeters, it's 4.7. These 3 readings can be plotted on a graph, and they produce a curve. This is a logarithmic curve, and if the readings are plotted on log graph paper, a straight line is produced. And you will see that this straight line cuts the vertical axis at a height of 1 millimeter above ground level. This means that immediately above the sand on this beach, there is a zone in which there is no wind, a zone which is here no more than 1 millimeter thick. On an open beach, it's so thin that most grains project up through this zone of no wind and are rolled forward like this. And if a grain hits a slow-moving grain, it bounces into the moving air which carries it forwards. When it lands, it explodes other grains upwards, causing these too to be moved downwind across the beach. In this way, more and more sand grains will be moved until the entire surface of the beach appears to be in motion. This process is known as saltation, and it's the process which dominates sand movement. It's obviously dependent upon the strength of the wind, but the nature of the land surface is also important. Irregularities like this piece of driftwood can have a striking effect. It lies in the path of the wind, which is funneled around the edges, producing a dramatic increase in wind speed. This in turn produces a disproportionately large increase in sand transport. The result is erosion, as can be seen at the edge of the log. On the sheltered leeward side, wind speed drops. Its ability to transport sand is reduced, and surplus sand is now deposited. This might appear to be the start of a sand dune, but its growth is limited by the size of the obstacle. For true dunes to develop, a different type of obstacle is required, one which can keep pace with deposition. In short, vegetation. And vegetation does have a dramatic effect on the zone of no wind. If a hot wire anemometer is set up in dense vegetation, this becomes apparent. Remember, the readings taken over bare sand produced a very thin zone of no wind. In the grass, the readings give a line which is much less steep, and the zone of no wind is 10 times greater, and once saltating grains enter this zone, they tend to remain there. Consequently, sand accumulates rapidly. But under exceptional circumstances, sand will still move forward. The growth of some plants can keep pace with the rapid sand accumulation. Dr. Pethick again.
Now I'd like to show you that on this plant which I've collected. This is just one root of a plant, and here we've got at the bottom a line of nodes down here, and that shows that the dune surface was at one stage down there. Then it was swamped with sand and grew up through, and the second line of nodes is here. That was the second sand dune surface. Another swamping, the vegetation shot up through, a third line of nodes there, another swamping, and a fourth line of nodes there.
The sand accumulates around the grass and distinct ridges are formed. Once formed, these dune ridges are maintained by the movement of wind over them. This can be seen on this model. Wind velocity is obviously high over the dune ridges. Sand transport is rapid and erosion is likely. In the lee, the protection offered by the dune ridge reduces wind velocity and deposition takes place. The overall effect is to produce a wave-like pattern in the wind, and as a result, wind velocities are also high at the bottom of the valley between the dunes, the area known as the dune slack. In this way, the growth of the dune ridge is limited, and the level of the floor of the slack is maintained. Wind speed readings can be taken at regular intervals across the dunes, and for this, a simple handheld anemometer can be used. If these readings are plotted, the upper line here represents wind speed. The nature of the relationship between dune form and wind velocity becomes apparent. And it's clear that the present pattern of dune ridges and slacks will be maintained. If erosion continues on the dune ridges and deposition takes place in the lee of the ridges, the entire dune system will begin to move inland, with the result that the foreshore will be available for the formation of new embryo and foredunes. This entire dune complex is the result of the interaction between wind, moving sand, and vegetation. And in order to study it, a systematic method is needed. First, we establish a line of transect across the dunes from mid-tide level. This is laid out using surveying poles. At 5-meter intervals, the angle of the beach surface is measured using a clinometer. "100-meter-long survey lines are laid out along each of the dune ridges, at right angles to the line of transect. On each of these lines, sampling points will be located, in this case 5 on each survey line. For this, a list of random numbers is used. Choosing any point on the page and reading in any direction, 5 consecutive 2-digit numbers from 0 to 99 are chosen. These are then related to distances along the survey line. Starting here on the first line of dunes, they're known as the embryo dunes, 1-meter quadrats are laid down at the points previously identified. Since the aim is to locate the quadrats at random, these points can be located by pacing rather than by accurate measurement. Each quadrant is divided into 100 squares. Some quadrats cover completely bare sand. But this one is more typical, and here a species count is necessary. There are in fact 2 species of grass in this quadrant. If they were in flower, identification would be easy. Sand twitch on the right, marram on the left. But these specimens are not in flower, and identification is more difficult. Careful examination, however, reveals other distinctive features. This specimen has a pronounced ligule. A ligule is an extension from the top of the leaf sheath. This identifies the species as marram, Ammophila arenaria, rather than sandtwitch. Using this method of identification, we count the squares in which marram occurs, only 6 in this case. Sandtwitch, Agriparan junciforme, on the other hand, has no ligule. A count shows that it occurs in no fewer than 88 of the 100 squares, and is by far the dominant species on the embryo dunes. Next, a soil sample is taken for later comparison and for analysis in the laboratory. It's important to number each specimen clearly. The pH of the soil is measured. In this case, it's little more than sand. For this, a field testing kit can be used. A small amount of the soil is placed in a test tube. The tube is then topped up to a predetermined mark with distilled water. To this mixture is added barium sulfate, which clears the suspended solids. And finally, a universal indicator is added. This causes a marked color change. The color can then be compared with the standard colors given on a soil indicator chart. In this case, the blue is darker than any on the chart, indicating a pH of over 8. This is a highly alkaline soil, probably as a result of the calcium carbonate in the shell fragments which are plentiful here. The dominance of sand twitch in this situation can be attributed to its ability to extract fresh water from seawater. Inland, from the embryo dunes, the line of transect rises. This is the foredune ridge, a line of low dunes, little more than 3 meters above the level of the beach. This change in height, small as it may appear, produces a very different environment, and this is reflected in the vegetation. Quadrats are again laid out at random along the survey line, and this time they tell a different story. Sand twitch is still important. You can see it flowering here, and it's found in 49 squares of this quadrant. But its dominance is now being challenged, and marram is found in 41 of the squares. This is a reflection of the change in environment. Conditions are now much more arid. Because of the increased height of the dune ridge, incursions of seawater are rare, and rainwater quickly passes through the sand. And sand twitch is not so well adapted to survive in such conditions, although it helped to create them. The foredune ridge, small as it is large enough to modify the flow of wind over it. Sand movement is again rapid on the ridge, and the absence of vegetation in the hollow behind the ridge is an indication of the strength of the wind there. The line of the transect now rises very sharply onto the first dune ridge, which is 17 meters high. This is the most impressive feature of the entire dune complex, dwarfing the foredunes and embryo dunes, and forming a major obstacle to the movement of sand. It also provides a harsh environment for plant growth. It's exposed, arid, and windswept, an environment dominated by one species. Marram is found in every square of this quadrant. The comparable figure on the foredunes was 41%. Its dominance can be attributed to the way in which the plant is adapted to such an environment. For example, one side of the leaf has many ridges which protect the plant's stomata. And to prevent water loss through the stomata during dry weather, the leaves fold like this. The front of the leaf is then exposed to the wind and sun, and since this is smooth and shiny, transpiration is reduced. And, as further protection, each leaf acts as a weather vane, aligning itself with the wind, thus reducing the surface area exposed. This produces these distinctive marks in the sand. The effects of the large first dune ridge are felt far inland. Not only does it offer shelter from the worst effects of the wind, it also acts as a physical barrier between the interior dunes and the beach, greatly reducing the movement of sand inland. Sand movement obviously still takes place on a large scale on the crest of the first dune ridge, where wind velocities are often high. But deposition is equally rapid on the leeward slope, particularly where the cover of marram is dense. As a result, the movement of sand inland is greatly reduced, and the results can be seen along the line of the transect. The second dune ridge is noticeably smaller than the first, and each succeeding ridge is smaller still. And the vegetation reflects these changes. Here, on the second dune ridge, marram is less conspicuous. It depends upon supplies of fresh sand, which are no longer so plentiful. And new competitors have appeared, many of them benefiting from the shelter offered by the marram. All taking advantage of the organic or humus material which marram has contributed to the soil, and the increased amount of water stored in the soil. The effect can be seen in the first quadrant, which is much more varied. This is red fescue, Festuca rubra. Like marram, it's a grass, but the leaves are thin to reduce evapotranspiration, and the seed heads are produced on long stems to help pollination and seed dispersal. Sea spurge, Euphorbia paralis, has other ways of coping with drought conditions. Thick, fleshy leaves to retain moisture, and in hot, dry weather, the leaves close together, again to reduce transpiration. And this is how mouse-eared chickweed, Cerastium fontanum, responds to the environment. It dies down during the summer, and its seeds remain dormant until the autumn. And during the wetter winter, it forms a small rosette, like this lesser hawkbit, Leontodon taraxacoides, growing close to the ground in the zone of no wind, where water loss is much lower. Beyond the second dune ridge, the decline is more obvious. They are known as the wasting dunes. They are lower and much less impressive. There is little fresh sand available. Marram is beginning to die out, and many more species are to be found. Some of these, like creeping willow, Salix repens, are water-loving and probably originated in the slacks which lie between the ridges. These slacks are now much wider. They're covered by dense vegetation, reflecting the fact that the water table is now near the surface. This, in turn, prevents further erosion, even when winds are very strong. Here, for example, the ground is waterlogged, and this is fresh water, possibly floating on salt water beneath. And the vegetation is obviously marsh vegetation, with yellow flag irises, and reeds and rushes conspicuous. As we have seen, some species have colonized the lower dune ridges, although the greater availability of water and the higher organic content of the soils means that many plants can cope with the environment there. And here on the fourth dune ridge, for the first time, shrubs and bushes begin to appear, like this sea buckthorn, Hippophae rhamnoides. All those changes have taken place within the space of 400 meters. And they are changes not only in vegetation, but also in the nature of the underlying soils. Here are two of the samples which have been taken along the line of the transect. One from the embryo dunes is almost pure sand, containing virtually no organic material. The other, from the fourth dune ridge, is much darker, indicating a higher organic content. And there have been similar changes in pH values. On the left, the dark blue color, indicating the high pH values found near the beach, with lower pH values on each succeeding dune ridge. All four ridges have developed within a comparatively short time. Old maps show it to be within 200 years. And if the existing balance continues, new dune ridges will develop on the foreshore. But the balance is a precarious one, and slight changes in the environment, including the use of the area by man, can destroy large parts of the system. And this massive blowout here in the Ainsdale Dunes bears witness to the fragile and complex nature of the relationship between vegetation and sand.